Hello everyone, 6 p.m. at PST. Let's get started. Today, day 25, and we are almost there at the end of this semester. We have two more lectures to go. I put them in a miscellaneous bucket as a module. One is that today's topic is floating point representation. So far, we have discussed about the integer operations in details, and we assume that this MIPS processor that we are programming has the integer capability only. But definitely the real world is not satisfied with the integer values only, right? Almost everything is a real number, right? Be it your grade point, be it your bank interest rate, be it a scientific calculation, name it. Majority of computation is on the real numbers, and floating point representation touches a little bit about how these values are represented within the computing system, and also gives some introductory sneak peek about the instruction that you can use to manipulate the floating point numbers. And just remember, these floating point instructions are executed in a separate processor. We call it a coprocessor. It is not part of the main processor, but it is a different one which specifically deals with running floating point algorithm for addition, subtraction, multiplication, division, etc. So they're the specialized hardware in that sense. Um, then what you need to do, focus about that. Oh, okay. Difference between this scientific and normalized notation in the floating point, not floating point, that number representation. This is important because like floating point representation inside the computing system has been derived from the normalized notation. So we have like general representation of the real numbers, then we have scientific notation, then we have more restrictive normalized notation. And normalized notation, you can think the floating point representation is a normalized notation as a binary patterns. So that part you need to be very much clear about. Also, please make sure you understand the IEEE standard format, like given a like 32-bit pattern, uh, what that pattern represents, what real value that pattern represents. It's mainly the bias exponent IEEE format, and also understand implication of the underflow error, rounding error, comparison of the floating point data representation. In some cases, you'll be surprised to see the issues and bugs comes from not handling the floating point numbers or real number in a high level program properly, like be it a comparison, be it a cumulative rounding error, and so on and so forth. Uh, so that part, as a programmer, you need to basically be aware of when you are writing applications and programs for crunching the real numbers. All right, saying that, any question, specific one from this topic or any other topic? Let me see.
Professor, I actually had a question about the project.
Yes, Ricky, tell me.
Uh, so in the assignment page for the project, you wrote down to please check each operation result manually from output.
Mhm.
I was wondering what you meant by that. Do you mean like we should create our own test cases, or should we?
Uh, I would encourage to create your own cases as well, but there, what I mean, you see that this program compares result between the normal ALU, that procedure, and your logical ALU, and if they are same, it says it's a pass. But in some very corner cases or very tricky situation, it might happen that your both normal and both ALU logical is giving you the same result, but they're wrong result, right? For example, very hypothetical case, right? you are wrongfully, let's say it is an addition operation, but with some bug, both your normal and your logical implementation is returning your subtraction value. So this test program will tell, hey, that passed because both are same. But in reality, they are wrong because instead of addition, they're returning subtraction result. So that's what I want you to actually manually, go and check, okay, 40 plus 3 is 43. Really, that's the 43 or not. Does that make sense,
Awesome.
Ricky?
Yeah, it makes sense. Thank you.
Okay. I think one there is from Chirag uh, on the discussion. I answered that already. So as far as the overflow is concerned, you don't need to worry about the overflow in the ALU. You do not need to catch them. Only part the overflow is mentioned there when you are computing the 64-bit 2's complement. There you need to change the addition procedure to return the carry out from the last stage, which you can think as overflow bit or for the adder. But anyway, though, nonetheless, this is the last carry out stage. You need to capture that and return that in the V1 register. So that's the only part that probably you need to little bit worry about that carry out. But not really like overflow detection. No, you don't need to. Okay. Anything
Professor?
else?
Professor,
Yes, Rahul.
I have a question. It's a technicality question.
Mm-hmm.
What's the difference between a procedure and a function? I've kind of heard them both being used interchangeably for the same set of instructions that include frame creation, operation, and frame restoration.
That's a very good question. So, like by definition, a function is a procedure which returns values. Like, um, or you can say like, yeah, I'm not a very like linguistic expert, like computer language expert, but I would say that there is this functional programming, right? This is that as like a Scala or what is the Lisp. Those are the functional program where you actually represent everything in terms of a function, which is like a mathematical operation returning back you some value. Okay, whereas procedure is not something that returns you the value, but manipulates information which is stored in the memory or disk, and it's kind of uh, like step by step process data crunching on that. So in a very top level, that's the difference. But if you really need to want to know about the like really detailed theory about that, you probably want to ask some language teacher, like computer language teacher, for formal
Okay,
difference of the between function and procedure.
so for the purposes of the report, if I have written them interchangeably, is that all right?
Yeah, that's fine.
Okay.
Yeah,
Perfect.
we
So
too, like in industry we use it very loosely and
I
interchangeably
see.
as in like function, procedure, method. Like in the object oriented context, we call it a method. A method can return something or may not return something. So yeah, probably a language teacher can give you more formal definition, stricter difference between those two. Okay.
Neat. And another question I have, just keeping my previous knowledge clear, the difference between jump and link and jump is that jump and link first stores the present program counter to array and then jumps. Is that it?
Yes, program counter plus 4. It's stored
Huh,
the next
plus four.
instructions. Yeah. Yeah.
And that's it. I see. Oh yeah, and one more thing I just remembered.
Mhm.
This is regarding the what's it called? Our report is about our I mean the language styles. Like if there's a statement where we're talking about results being tested, is it all right to say I tested the results, or would you prefer it to be like the results were tested?
Yeah, that's fine. Yeah, we're not
University.
that strict about the language of the report. But ideally in industry, you probably want to do more passive sentencing than active sentencing, but that's okay.
All right. Thank you.
All right. So then let's do a problem. Okay. Let's do a problem. I'll just give you step by step of this specific problem. Let me see. Okay, screen share. Okay, so this problem is telling you that we have a little piece of code which involve floating point, and of course we haven't learned what is a floating point different instruction does, but let's see how we can manage it. So we have two bit patterns stored, right? This is, let's say, in the some memory location var1 and var2, and then we have some unfamiliar instruction operation going on, LWC1, LWC2, etc. Add dot s, and then another set of unknown thing is saying that okay, there is a system call which is system operation, code is 2, okay, on the v0. So this basically to print any floating, to print the corresponding floating point number on screen from the F12 register, $F12. Now let's see. So here the question is, at the end of this program, what number will be printed on the terminal? Because it's something to do with the this number printing as a floating point number, and which is stored in the F12. And you see that everything is actually operated on F12. Sorry, final result. This is the F12. Now, what is these instructions are? This is easy to find out. You go to your MIPS reference data sheet and look at this part, right? This section. It is giving you kind of summary of available floating point operations in the MIPS coprocessor 1. And we first let's look at this LWC1. LWC1 is right here. It's saying that load the floating point single. Okay, so LWC. So it's basically it's a read load word operation, but instead of loading it into the main processor, it loads into the coprocessor 1 onto the target register. So here, in that sense, it is reading from this memory location and loading into the coprocessor register $F1. Okay, so this part will be loaded into F1. And then this word, this bit pattern will be loaded into F2. And then you are doing an add.s. Now let's get back to that page again. So what is add.s is this one. Floating point add single means it's a single precision operation where it's the same add operation, but it is doing a floating point addition instead of integer addition. So these bit patterns will be treated as a floating point value, and this addition will do that floating point value addition and put the corresponding bit pattern onto the F12. And then this syscall will print that F12, whatever that bit pattern represents, that value represents. So that's the program doing. So practically the challenge here now is to determine what floating point values these two bit pattern is representing, right? So that's kind of easier problem now, since we know the IEEE format, which is given onto the next page. See the single precision, it's a -1 to the power s plus 1 plus fraction 2 to the power exponent minus bias, and for single precision bias is 127. So saying that, let me just put it a little bit aside somewhere. All right, so here, format-wise, we have these 32 bits are broken down into sign, exponent, and fraction. This bit pattern, total 32. So sign is 1 bit according to the format, right? This is the 31st bit or 32nd bit is your sign bit. And from bit 23 to 30 is your exponent. So 23 to 30 is 8. Right, 8 bit, 23, 23, yeah, 8 bit. And then rest of them are fraction. So rest of them would be 23 bit, right? Is a 23 bit, yeah. 0 to 22, 23 bit is your fraction part. Now, given this hex 32-bit pattern C0 6F 8000. So this one, if we change it to 32-bit of 32 bits, right? Let me change the font. Okay. Now this number is C. C is ABC. C is 12. 12 is 1100. Then 0, which is 0000. Just hold on. Yep. 0000. Then 6 is 0, 110. Then F 1111. Then we have 8 1000. Then we have 3 zeros. 000 000 up 4 zeros. Okay, maybe this is too small. Let me just here. Okay. So we have 4, 8, 12, 16, 20, 24, 28, 32 bits. All right. Now we have this bit pattern, and we know my sign bit is the most significant one, which is this part. And then comes the exponent, which is 8 of them, right? This is 7, 8. All right. And then the fractional part would be the rest of them. So this is your fractional part. So just to make sure. So we have, let's see, 3, 4, 7, 8 bit for exponent, 1 bit for sign, and 4, 8, 12, 16, 20, 23 bits for the fraction. So here, then you can say that your S, in this case, your S equals 1, then exponent is like 100, that 8-bit pattern is, this is a unsigned value, which is 128, it represents. And fraction, let's just keep it in binary for time being. 110, 11111, and rest of them is 0. So we know that, yeah, rest of them are zeros, bunch of zeros. So now from here, what we want to do, we explore this guy. This is your formula, right? Exponent this. Let's keep that handy. So somewhere. And for this case, this is a single precision. Your bias equals 127. Okay, so now we are ready to do the math here. So your value
Professor,
is, yes,
I have a question. How is 0 represented in floating point?
0.
Yes, how is
It's
0 represented?
so 0 is basically, if you think uh, these are okay, that's a good question.
I kind of noticed we were using the most significant bit as an indicator of positive, negative, and I remembered we did not do that in the previous in with integers because that gives a redundant 0. This was one of the reason, and so I thought about it over applying it over here, and I realized, wait, I don't know how to put 0 over here.
Right. Uh, so that's a good question. Let me give a thing. Okay, I'll come back to you. Okay, on that zero representation. Okay, let's solve this problem first. All right. Okay.
All right.
Okay. Now let's calculate this one. So your value is really is saying, okay, this is is that it's to the power. So your value is really here. S is 1. So minus 1 to the power 1, because this is the 1, S equal to 1, multiplied by 1 plus fraction. Here it is means we are talking about 1 plus 0 point, then rest of these patterns. Okay, 0 point something. So these patterns comes up here. Okay, 1 1 0 1 1 1 1 1. Let's just stop there. Okay, into, okay, I missed, it is the to the power, into 2 to the power of exponent minus bias. Our exponent is 128, bias is 127, then it is that value. So this one, okay, just do it. Now this one would become like minus 1 to the power 1 is minus 1 multiplied by, let's keep that bit pattern, binary bit pattern as it is. Okay, this is like 1 point, 1 plus something is 1 point, rest of the pattern. Okay, and multiplied by, it is 2 to the power 1. Okay, so this means your number would become like, it's a negative number, negative 1 1. So it is basically multiplied by 2, right? Multiplied by 2 means you are shifting the points to one place. Okay, so basically you look at the power of the 2 and you shift that decimal point towards the right if it is a multiplication. So that's what being done here. So this becomes 1 1 dot 1 0 1 0, then 1 1 1 1 1. This is in binary. Now what is the corresponding decimal value? It will be like, this will be 2 plus 1 plus, just to strictly speaking, it is 2 to the power 1 plus 2 to the power 0 plus 2 to the power minus 1, okay, plus 0 for that 0 part, plus 2 to the power minus 3. Okay, 2 to the power minus 1, 2 to the power minus 2 to the power minus 3, plus 2 to the power minus 4, plus 2 to the power minus 5, plus 2 to the power minus 6, plus 2 to the power minus 7. Now these are all in decimal format, and then use a calculator. It will become something like 3.7421875. So this bit pattern represents this decimal value. So we did do the same thing for the other bit pattern. So which is like 0x400A8000. Okay, which is basically we just expand them into binary bit pattern. So this is 0 1 0 0, that is 4, then 0 0 0 0 0 0 0 0. A is 10, 10 is 1 0 1 0, then 8 1 0 0 0, then 3 zeros. Okay, so now again we divide them into our fraction, which would be okay, let's start with the sign. Then we have the exponent, which is 3 4 7 8. Okay, then we have the fraction part there. So here in this case, our S is 0. We can well imagine this is a positive number, and then your exponent is 128. Okay, 128, and fraction is 0 0 0 1 0 1 0 1 0 0, and rest of them are 0 0 0. Okay, now saying that, then my value is minus 1 to the power 0 multiplied by 1 plus the fraction part. Fraction part would be 0 0 0 0 triple 0 1 0 1 0 1. Let's just stop there. Multiplied by 2 to the power 128 minus 127, the bias. So this minus 1 to the power 0 is 1, multiplied by this 1.000100101 multiplied by 2 to the power 1. That really means 10.00100101. Now change it to the decimal, translate it. So it will be 2 to the power 1 plus 0 plus 2 to the power minus 1 minus 2 minus 3, 2 to the power minus 3, then 0, then 2 to the power minus 5, 2 to the power minus 7. That will give you 2 plus 0.5 plus something, which ultimately if you use calculator, it will come down to be 2.1640,625. So now we get both of them. both this pattern and this pattern's values. Now it's a matter of addition of these two values. So my F12 $F12 at the end of that addition statement, it will be basically minus 3.7421,875 plus 2.1640,625, which is, if you use calculator, and then it will come down to be 1.578125. So this number will be printed on the terminal through this syscall. Since F12 has a bit pattern that corresponds to this value, it will print that 1.578125 on the simulation terminal. Question?
Just real quick, I wanted to make sure the bias number, was that a given or where did we get that from?
That is by format. Bias
Yeah,
is all,
okay.
yeah, 127 for, yeah. Okay. Rahul, coming back to your zero question, I think zero is a special bit pattern. Zero is a special bit pattern where your exponent part and fraction part are zero. Basically, all bits are in F are zero. E is zero. It's basically that zero. It represents the zero. In fact, it has three more special representation. One is called a plus infinity, minus infinity, and not a number. Not a plus infinity and minus infinity. They're basically sign bits at 0 and 1. An exponent is 255, and fraction part is all 0. So they are positive infinity and negative infinity representation. And NaN is exponent is 255, and fraction is has at least one non-zero bit. Any non-zero, doesn't matter which bit is non-zero. But if the fraction part has non-zero, an exponent has a bit pattern 255, sign bit doesn't matter. It's a NaN, not a number representation in the floating point format. Okay.
Okay. I see. So depending on which combination is used for zero, there is one particular floating point number which is unavailable to use.
In fact, a lot of floating point number are unavailable. Because but theoretically there is like infinite number of real
Yeah,
numbers
there is that also.
between two integers, right? So
Yes.
that's one point we always need to keep in mind when we are dealing with the floating point or real numbers, is that not all the values are representable to the accurate decimal point. Okay, there would be some value truncation always to the result of the floating point operations. So it's kind of what we see and get from computing system on a floating point result is an approximation of the result. And there it comes your supercomputing, where it basically like programmer can control. I want probably like 1,000 decimal place accurate representation of my value. Remember the famous real number pi? Its value is still being crunched. It is still having a new value pattern there. So one computer crunching the real bit pattern value that should represent the pi, and it is still being computed. So not all the numbers is representable with a floating point representation. If we need more precision, we go for like from single precision to double precision, which is means that instead of 32, we go with the 64-bit. If 64-bit is not even sufficient, we want to go with the 128-bit representation, then 256-bit representation, whatnot. All right.
So, wait, is there a way to represent greater decimals taking advantage of the stack?
Come again. Sorry, I couldn't hear you. I barely hear
I'll
you.
repeat that. Is there a way to take advantage of greater what's it called? Uh, Take advantage of the stack to get greater precision using the 32-bit or 64-bit?
Like
We do
using
that
the
for parsing
stack.
out. Yeah.
Yeah, definitely, right? If you want to represent things with more than like 64, 128, you can ingeniously like use your stack, available stack to represent like maybe 256-bit floating point or things like that, right? You
Okay,
can,
so
you
it's a
can.
possibility. It's not like a general practice or anything.
It's not a general practice. Like we have found in all practical engineering purpose, 64-bit representation is more than enough to carry on. Like unless, yeah, supercomputers are for really precise scientific experimentation, maybe for rocket launching space. I don't know if they use a supercomputing and more precision bit, but in general, like in your banking field, in the electronic design automation, electrical analysis field, 64-bit is sufficient so far, accuracy wise.
All right. Thank you.
Okay. All right. Why don't we take a 5-minute break and then we'll be back? Be back. 5 minute means about 6:40, 45-ish, 6:45-ish. We'll be back. Okay, let's get back and time for pop quiz. If you go to your, please go to your canvas. There is, we'll find some pop quiz 7, and let me know through the poll if you are ready to enter the quiz password. 2 of 16, 3 of 16. Fifteen of 16. I'll wait a couple of more seconds and give you the password. Okay, here it goes.
Hi, Professor.
Yes, hello.
Hi. My browser accidentally closed. And I forgot the password. Could I get it? The password?
Okay. Don't you see the polls yet? No.
No, I closed out of it when I was doing my quiz.
Okay. Let me see if I can send it over chat.
Sorry, I know I had the same problem yesterday.
So what's your name again?
Aditya?
See if you can use it.
Yep. Thank you.
Okay. Okay. I think most of your time is up. Anyway, so is there any questions, concern, comments, or we can stop tonight, Ardi?
Hey, Professor.
Yes.
For the project, when you want to set one register to another, is it okay to use add as an operation? Should we be using move or?
That's a good question. If you want to, move content from one to another?
Because what I've been doing is using add and then the second register, then register 0 to.
Okay. I'm just thinking. Try add I with immediate 0.
I mean, like it's working for me. I just don't know if that's allowed for the.
Yeah, or maybe you can do the move with the pseudo command. Use
Okay.
that.
I'll use move instead.
Yeah, I forgot like our evaluation automation. If it actually looks for specific instruction, arithmetic instruction in your implementation.
Yes.
So yeah, so I would avoid add those kind of keywords there in that program. But using the move pseudo instruction should be.
Sounds good. Thank you.
Wait, Professor,
Yes.
if the project, I mean, if the project is partially auto-tested like that, it's just looking for the keywords, then how is it going to be all right if we use an add for the loop to keep track
So
of the loop?
I think add I is exempted from that list? Yeah, you can still
Okay.
use add I, not add.
I see.
Yeah, but anyway, if there is an like deduction that you think it is not valid, you can always communicate with me, and I can always manually check.
I see. Thank you.
Okay. Is there any other question, comments, queries? All right, then good night, everybody, and see you on Thursday. Make sure you turn it next Thursday. This coming Thursday is your project submission deadline. Make sure you are working towards that. Don't be late.